Most textbooks show the solar system as a neat row of 8 planets, evenly spaced across a single page. That illustration creates a false sense of proportion. To understand the actual layout, we must look at the true gravitational center. The Sun accounts for 99.86% of all available mass in our system. Everything else, every planet, moon, and asteroid, is constructed from the leftover 0.14%. This yellow dwarf star operates as an immense nuclear furnace. It has been burning for 4.6 billion years, driven by a core temperature that reaches roughly 15 million degrees Celsius. The solar system is a raging star surrounded by a tiny fraction of gravitationally trapped debris. Shrink the Sun's 1.39 million kilometer diameter to a basketball. Earth becomes a pea 26 meters away, the first zone harboring biological life. Neptune lands over a kilometer away. Light, traveling 300,000 kilometers per second, takes over 4 hours to cross this gap. To understand how planets form, we must travel outward across this 100,000 astronomical unit radius, where 1 AU is the distance from Earth to the Sun, and observe exactly how extreme distance alters physical matter. The closest region to the star is the inner terrestrial zone. This tight orbit holds Mercury, Venus, Earth, and Mars. These 4 worlds are small, dense, and rocky. During the system's earliest formation, the immense heat near the Sun meant that only heavy, high melting point materials, like metals and silicates, could survive to coalesce into planets. Yet similar base compositions yield wildly different surface environments. Venus is a toxic atmospheric oven baking at 465 degrees Celsius, sitting right next door to Earth's biological balance. Further out, Mars presents a landscape of extreme geology, hosting Olympus Mons, the tallest volcano in the solar system. Extreme proximity to a star allows heavy, dense planetary cores to form, but it leaves the resulting surface environments highly volatile and radically distinct from one another. Past Mars, we cross the asteroid belt boundary. This region contains millions of metallic and rocky objects, ranging from dust particles to bodies nearly 1,000 kilometers wide. This debris is remnant material from the early solar system. It sits here as a graveyard because the massive gravitational pull from Jupiter prevented these fragments from ever fusing together into a single planet. Look at this image of Saturn to see the scale shift that happens next. Out here, Jupiter and Saturn operate as gas giants. They lack solid surfaces entirely, composed primarily of churning hydrogen and helium. They also dominate their local space, creating complex orbital neighborhoods. Jupiter anchors 95 known moons, while Saturn is defined by the intricate ice and rock composition of its massive ring system. Pushing further into the dark, Uranus and Neptune fall into a different category: ice giants. They hold higher proportions of frozen water, ammonia, and methane, driving extreme weather phenomena like Neptune's 2,100 km/h winds. Beyond the inner heat zone, planetary bodies trade solid ground for immense mass and turbulent atmospheres, effectively acting as chaotic mini-solar systems of their own. Pushing past Neptune, the system opens up into the Kuiper Belt, a vast expanse composed mostly of icy objects. This is the domain of dwarf planets like Pluto. These icy bodies possess enough mass to pull themselves into a near-spherical shape, but they lack the gravitational dominance to clear their orbital paths of other debris. At the absolute outer boundary lies the Oort cloud. It forms a massive, spherical shell of icy bodies in a deep freeze, occasionally throwing inward the long-period comets that streak across our night sky. This 100,000 astronomical unit boundary is a pristine, frozen reservoir holding the exact chemical building blocks left over from the gravitational collapse of our solar nebula. For the last 70 years, humanity has built the technology to cross these distances and map the architecture firsthand. We have landed on the inner terrestrial worlds, using robotic rovers to actively drill and analyze alien geological samples on fractured Martian bedrock. Next-generation space telescopes continue to look outward, gathering light to resolve the chemical and atmospheric mysteries of distant, otherwise unreachable bodies. We have also reached the ultimate geographic milestone. Probes launched in 1977 survived the entire outward journey, pushed past the Oort cloud, and successfully pierced the boundary into interstellar space. Mapping this dynamic 4.6 billion-year-old structure provides the universal blueprint for planetary formation, revealing the chemical and gravitational history that produced the world beneath our feet.